However, if saying I don't like these configurations, I want to see the distribution of the stress in a different configuration, in different orientation of the stress element. And at the same point, and I might try is this, say, I don't like this orientation, but I like is in these orientations. Again, here I overlap with another stress element, but here you can see we have a different orientation. On the new orientations, I want to know what is the distribution of the stress, for including the normal stress and the strain stress. Okay, and don't ask me why, but the reason is this: we might have certain design considerations. We have to consider the distribution of the stress in such an orientation. Okay, so the question is this: how to, based upon those given information, for example, the tau x, tau y, and tau xy, tau yx, those are the results based upon, for example, your homework, right? And point H or point K, and last time I showed you how to pick the stress element in the right angle aligned to the XY corner system. And based upon those results, we want to do the study of we want to calculate the value of the stresses in a different orientation. And that orientation, for example, we given a certain value, any value, say theta. So the problem statement becomes like this. Many times, if we overlap drawing of the two stress elements around one point, it will be very messy. So in textbook, actually in solid mechanics, our the practice is this: we try to extend the oriented element away from the drawing here, try not to overlap, but they representing is the same. The distribution of the stress about the same point. So in this way, the good exercise is this. Let me repeat here. For example, if this is a point, and here is the originally given the element. So here is sigma x here. Let me repeat, sigma y and tau xy, tau yx. So here you can see in this drawing, I use this as the magnitude. Okay, so this one representing is the magnitude of this and this. They are equal. Using this one. So I try to simplify the whole writings. So here again, let me get rid of this one. So those are the given informations, and then to represent the distribution of the stress in an oriented element is this. From here we extended the drawing not to overlap, and then from here. In the new oriented element is like this. Okay, so this one has the angle. For example, here between the x-axis, we define the angle, say any angle theta. And then in this new orientations, respect to our originally defined coordinate system, here we define say x prime and y prime. In the new orientations, we are interested in looking for sigma x prime, that is a normal stress corresponding to the new oriented. So that is sigma x prime, and here is sigma x prime, and here is sigma y prime, sigma y prime, and the same thing we have the tau x prime, y prime, the same thing here. So that is the distribution of the stress in the new oriented the stress element. So the problem statement is this: we are given, based upon your homework, the combined loading, we are given the sigma x, sigma y, tau xy. So those three values, for example, again from your homework, chapter 8. And then we want to know for any orientations that I designate, for example, theta equal to 30 degrees or 45 degrees, and then your job in these chapters is going to calculate what is the value of this So the three quantities representing is the distribution of the stress in the new oriented element. And those three quantities will be the function of 1, 2, 3, 4 values. And those one we call, and those one is called the transformation of the stress from the given one by a certain orientation to the new one. So that is in these chapters we talk about the transformation of the stress actually is to solve these problems. Okay, so any questions? So that is the big pictures of these chapters. And there's two approaches. The method one is do the by theory, by formula. Formula is based upon the equilibrium equations. The second one is by using more circle. And we're going to go over the both methods. And either one will give us the same result. And so for the testing, otherwise indicated, you can use either way. Okay, on your cheat sheet, I provided the formula on your cheat sheet. So that means in your, say in your test, you might be able to use formula. But here I want to give you a warning. To apply the formula, we have to memorize sign conventions. Again, one more time, sign conventions for what is a positive for each stress component and what is positive for theta. So I'm going to go over. So probably, hopefully today I can finish the formulation today and then do exercise. By Friday, I want to finish the more circles method. The more circles method is the very powerful, and this more circles method not only apply to the stress, the transformation of the stress, but this one I believe you have learned in your statics. More circles method can also apply to calculate the moment of inertia, the principle of moment of inertia. Okay? You know what I'm talking about? The IXY. IX, IY, something like that. Okay, so those one, basically this one is applied to the tensor of rank 2. Stress is one example of the tensor, with the tensor of rank 2. The moment of inertia is another example, and strain, and we put another one. But anyhow, here we talk about is the formulas. Okay, so here we go to the formulas. Transformations of stress. So again, here let me not repeat the whole things, and I'm going to write up the formulations. The formulation is this. We're starting from graphics. So this is a stress element. So this is xy. And let me draw this one again. Sigma. You better to draw this bigger, about 1 inch by 1 inch on the sides, okay? And because there's quite a bit information. And sigma x, sigma y, and magnitude of xy. And again, I want to emphasize one more time. Here I labeled is the magnitude. Okay, here is the magnitude of those 4 strain stress components, but they 1, 2, 3, 4, the 4 strain stress components they are different quantities. Okay, they are different. So now for this case, then I can build up is this. For example, let me try to calculate what is the stress distribution along this phase. Okay, so that is my first step. So here, for this line, that is orientation. The stress distributed in the plane oriented like this. I want to draw this oriented plane onto here. So that means, let me say, try to do this. So let me align that plane in such a way, like this. So this angle is theta. Okay, if you compare this one carefully, then you can right away to know this angle should be equal to theta. And again, our goal is to calculate what is the, for example, here, right now I'm focusing on the distribution of the stress in this oriented plane. So that means at this moment, I want to calculate what is the two components. Okay, so here I highlight using this one. So let me do this one more time again. So let me get rid of those things. So let me right now take the Friedman diagram of this triangular component. So on that triangular component I have is this. Okay, so on this one here, our stress is here. We have sigma x, and again, the stress is the force per unit area. So it really doesn't matter how big the size of the cross section is, the stress value will be there, not changed. Okay, so here we have sigma y, and here is the value of tau xy. Okay, so again, the value of the stress doesn't matter the size of the area you be on. Okay, so here is our angle theta. And now we're looking for is the distribution of the stress. So which means on this plane we have this one. And again, I just erase it. This should be prime direction. And this one is tau x prime y prime. Okay, so here, okay? So this is about the stress. So here for this drawing, we draw is about the stress. This is 90 degrees. And again, everything must be in static equilibrium. So right now, static equilibrium is equilibrium in force. Okay, the equilibrium in force. So I want to, based upon the information, to build up the equilibrium equation on force. So to do so, that means if we would have another information about the area, then I can multiply corresponding stress to area, give me the force. So here, let me draw the same element. And now for this one, I want to show is the area. So for example, here, let me say this area, say this one has an area, the magnitude equal to, say, 1. How about that? Okay, if this area, assuming that is 1, then this area is how much? Sine theta? And this area is how much? Cosine theta. Or if you like, you can say this one is A, then everything will be scaled up by A. Okay, so this is area. So then with the corresponding stress multiplied with area equal to force. So that means here we have the distribution of the force on this element, on this triangular element, on which we can apply the equilibrium equations. So here we do this one carefully. So, so this way, let me draw this one here. So the multiply will be sigma x prime times 1. So that is a force. So here the tau x prime y prime times 1, that is a force. And then on this side, we have, here I want to draw a bigger one because I want to later on do the projection of the components into x and into the two components. So here is, again, the sigma times area will be sigma y times sine theta. That is the force contributed by this stress on this side of the area. Okay? and then this one will be equal to tau, the magnitude tau xy times sine theta. Okay, and then this one will be sigma x times cosine theta, and then this one is tau xy cosine theta. So now you can see those are, right now here, all the information we're showing in this block, in this force element about the force. And everything must be in static equilibrium in two directions, right? So here, how many unknowns? We have two unknowns, and we have two equations. So we should be able to solve for the information. So here, let me label this carefully. Here we have two corner systems, either in xy, or here we have x prime and y prime. So here, if you want to take the equilibrium in x direction, y direction, or taking equilibrium equation in x prime and y prime, either way will be okay. Okay, so let me take equilibrium in x prime and y prime. That will be following up our textbook directions, the method. So here, let me do this. Sigma f prime equal to 0. So here we have to do the projections. So here, one side, and let me project this one carefully. For this one, okay, right now this is our x prime, this is our y prime. For the four components, I want to dig out the projections in each. So now we do this one carefully. Let me do this one. So how about this? We do this one by one. So now for this one, we summarize is this one, say tau x prime. Okay, so tau x prime will be equal to, with on this component, that will be how to do this one in a good way. So this will be the component of this one in the x prime direction. So that would be equal to, we fix this one, so that would be tau x y sine theta. So that is the force, and then we take this component, right? And that is how much? This is theta. So that is sine theta. Seems not correct. Let me do this carefully.
XY cosine where it's going to be sine.
Let me use this one as our sketch. And so this is xy, and this is x prime, y prime. Okay, so right now for this one is in these directions. So for that one, right now I try to fix this one. So this one is in this direction, so projecting into x prime and y prime, so that should be like this, right? So this is theta. So for this case, I think the beta drawing
You had
should
theta
be,
were different before. No, it was wrong before because your theta was different.
yeah, so here is a theta, right? Theta is the rotation
Yeah.
angle from between the two corner systems.
Yeah.
So this is theta. So if this, let me align that one, if this is xy sine theta, so this one, so this should be cosine. So here the beta drawing should be like this. Okay, so we fix this one. So this should be cosine. Got it? Yes.
Why are you not projecting into a direction that's perpendicular to the x prime, y prime axis?
Yes. So right now for this one, this is x prime, this is y prime.
Yeah, so why wouldn't you be taking the y prime, the smaller of the two values?
Oh, because right now for this formulation, right now I'm looking for the component equilibrium in x prime. And the next step, I will take the equilibrium in y prime. Would that be your questions?
Okay, yeah, I think I get it.
Okay. So now we use this one. So here,
I
with
have
yes.
a question. Why, in the first place, is it tau xy sine theta?
Because this is the stress. Stress multiplied his corresponding area is working on. So that's the total force. We want to calculate what is the total force on this side. So the stress multiplied with area. That's the total force. So this information on this blocking, on this drawing is about the force. Okay. So now we continue. So now